Bright QT. Every student matters.
Hello students, now let's do the questions for this portion. The first question is, how many isomers can you draw for pentane? Now pentane is a straight alkane with 5 carbon atoms. Pent means 5. So first let's draw the simplest possible structure and add hydrogens for all the valencies remaining. So this is called as N-pentane. It is a straight chain of 5 carbon atoms. Now one option is that we can remove one of these and put it here. This is the next form of isomer of pentane. This form is called as isopentane. The third form, I'll draw it here, will have 3 carbon atoms and 2 other carbon atoms on the middle carbon. That is the basic structure, and you fill the remaining valencies with hydrogen. This form is called as neopentane. Now these are the different ways in which pentane can exist in nature. These are all the isomers of pentane. These are their common names, and their structural names are different. This structural name would be pentane, and this structural name of there would be another hydrogen here. The structural name for this one would be, because it has 4, so it's a butane with a methyl group on second carbon. So it will be 2-methyl butane. This would simply be pentane in the IUPAC nomenclature. And the structural name again for this, according to the IUPAC nomenclature, because it is a 3 chain, the longest chain here is 3, it will be a propane atom with 2 methyl groups on the second atom. So it will be 2,2-dimethyl propane. So 2,2-dimethyl propane, because there are 2 methyl groups on the second carbon in this propane chain. This is 2-methyl butane and this is pentane. These are the IUPAC names, these ones, and these are the common names: the N-pentane, isopentane, neopentane. These are the forms of different forms of isomer for pentane. Let's move on to the next question. What are the properties of carbon which lead to huge number of carbon compounds around us? Now we've already discussed there are 2 main properties which give carbon this vast possibilities of structure. The first possibility is catenation. The second is tetravalency. So catenation is the property of carbon to form long chain-like structures, the ability of carbon to form bonds with other carbon atoms forming long chains, sometimes branched, sometimes unbranched, and sometimes even in forms of rings. That gives it a lot of possibilities. This is the first factor. The second factor is tetravalency. Because it has a valency of 4, it can bond with a monovalent, a divalent, or a trivalent atom in single bond, double bond, or triple bond, and that gives rise to even more possibilities of carbon compounds. So because of these 2 features, carbon has a lot of compounds all around us. What will be the formula and the electron dot structure of cyclopentane? Now cyclo means it's a ring, and pentane you know has 5 carbon atoms in it. So first let's draw a pentane ring. I've drawn it in shape of a pentagon. Now you see every carbon has a valency of 2 unfulfilled. So you attach 2 hydrogen at each end. Right, and that would give rise to the structure of cyclopentane. So how many carbon atoms here? We have C5 and we have H10. This is the structure of cyclopentane. So if you have to draw this in electron dot structure, you would change these bonds, and in place of these bonds you would put electrons. So let's draw the electron dot structure now. Carbon is sharing one electron with this element, one here, similarly one here, one here, one here. These are the sharings done with carbon. Now with hydrogen, we have one electron being shared here, one electron being shared here. Let's put the hydrogens also on here. I'm denoting the electrons of hydrogen with a cross. Now let's start drawing the circles around atoms to see if they have achieved the stable octet. Now this carbon was bonding with two hydrogens, so two hydrogens, these are here, and two carbon atoms. So you see it has 1, 2, 3, 4, 5, 6, 7, 8, 8 electrons. That's stable. This hydrogen has also achieved a stability by bonding with the with one electron each. Right? You see how these hydrogens are bonded. Now let's move on to this carbon. It has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Right? Now when we go on to this, before going on here, let's draw the circles for hydrogen. For hydrogen, it's very simple. They're just sharing one electron with carbon. Here we can also draw those structures. Right? Now let's draw it for the remaining carbon atoms. So this carbon is sharing one from here. Let me draw this more clearly. Right? Now let's move on to the next one. And the final one. I'm drawing this electron closer so it's easier to draw the circles around it. Right? So that is how the structure of cyclopentane would look. It's a little complicated in the terms of the number of circles you have to draw, but they're all single bonds, so it's relatively very easy. So all you have to do is draw this structure and remember to convert it to electron dot structure. You can just draw it and convert it afterwards. That will make it easier for you. Now let's move on to the next question. Draw the structures for the following compounds. First is ethanoic acid. Now ethanoic acid, so it means two. So we have C bonded with another C. It says oic acid. Oic acid means carboxylic acid group, which means there's a double bond O, there's a single bond O bonded with H. This carbon has filled its valency, and this still needs hydrogen to complete its valency. That is the structure of ethanoic acid, which is denoted by CH3COOH. The next question is bromopentane. So bromo means a bromine is added at the end of pentane. So first let's draw a pentane and attach a bromine at the end. Fill the remaining valencies with hydrogen. Right? So you see this is a normal version of bromopentane. And then question also asks you, are structural isomers for bromopentane possible? Now there are a lot of structural isomers for bromopentane possible. The first possibility would arise if we move the position of bromine from here to any other carbon atom. So if I had placed bromine on the first position, if I place it here or if I place it here, that would change the, that would also be an isomer of bromopentane. but I'm just putting it on the second position for now. And again, less positions fulfilled by hydrogen. Another option of a structural isomer of bromine can be when there's a structural isomer of pentane. A structural isomer of bromopentane can be when you make different structural isomers of pentane that you did previously. So we draw 4 chain. On the second one, we add a carbon. So this is 2-methyl pentane. We put the bromine here. Right, so this is also a different possibility of structural isomer of bromopentane. Even if this bromine was here or here, that would also lead to different possibilities of isomers of bromopentane. So there are a lot of possibilities of isomers of bromopentane. I've only drawn 2 here, and I've explained you the other ones. You don't have to draw them. You just have to give the answer of yes, where we could change the location of bromine, or we could also make isomers by changing the location of methyl groups. But if you were asked this question just for the first part, you will always draw the regular structure. The second one is draw the structure of butanone. Now, "-one" means ketone and "but" means 4. So we have 4 carbons and we want "-one", so that means there's a double bond O somewhere in the middle. So I'm choosing the second carbon. Fill the remaining ones with hydrogen. And that is the structure of butanone. The next is hexane -ul. -Ul means aldehyde group, which means a double bond O at the corner. So we have 6 carbon atoms, and at the corner we want an O. The remaining positions filled with hydrogen. And that is the structure of hexane -ul. So -ul means aldehyde, -one means ketone, which is a double bond O in the center. Aldehyde is a double bond O in the corner. Now let's move on to the next question. How would you name the following compounds? The first compound is CH3CH2Br. So you know that this has 2 carbons. That means we have to use the prefix of eth. So it becomes eth. Now it is because of its single bond, it is ethane. Because there's a bromine, it's bromoethane. So the answer becomes bromoethane. For the second part, it has C bonded with O. So this would be a double bond. I think that's a question mistake. And it has 2 hydrogen at the end. So because it's a corner atom in its own way, and there's only 1 carbon, it is methane -ul. The next part has 1, 2, 3, 4, 5, 6. It has 6 carbon atoms. So that means we are using the prefix hex. Now, it has a triple bond at the first carbon, which means we have to use the suffix "-ine". So this becomes hexyne. This is how you go about naming the atoms. You see how many atoms are there. You see if there's a functional group. You see if there's alkane, alkene, or alkyne, and then you put together the name to name the particular compound. The next question is draw the electron dot structure for ethanoic acid. Now, ethanoic acid has 2 carbon atoms. For oic acid, we have double bond O and OH group. And the remaining valencies, as always, with hydrogen. So it is CH3COOH. Right? These single bonds are represented here by sharing of 1 electron each. Again, here is also a single bond, and that is why there is a single electron sharing. When there's a double bond, two electrons are being shared in that pairing by both electrons. And here also, as there are single bonds, one electron is being shared each. As you see, every element here has a stable outermost shell. Hydrogen has 2, oxygen has 8, both these carbons have 8, and this oxygen also has 8. So that is how the stable configuration is achieved. Next is H2S. So H2S is very similar to H2O because S also has the same valency as oxygen, that is of 6. Sulfur has the atomic configuration of 286. And because it has 6 electrons in the outermost shell, it needs 2 more from sharing, and that it achieves by sharing with hydrogen. So as you see here, 1 electron is shared with 1 hydrogen each to achieve a stable structure. The next is propene-one. Now, one means ketone, which means a double bond O in the center, and we have 3 carbon atoms. Remaining valencies with hydrogen. You see, this is the stable structure, and you convert it into electron dot form, you get something like this. So hydrogen is sharing 1 electron each. The double bond O is shown by sharing of 2 electrons from each atom. And you see that all of them have achieved their stable outermost configuration. The next part is a fluorine molecule. Now fluorine bonds with fluorine as it has a valency of 1. So because of its electronic configuration and its atomic number of 9, it bonds with itself and shares 1 electron and forms a structure which looks like this. So that is for this question. Let's move on to the next question. Ethane with molecular formula of CH2H6 has how many covalent bonds? Let's draw the structure to understand. Now let's count the number of covalent bonds. It's 1, 2, 3, 4, 5, 6, 7. So it has 7 covalent bonds. The next question is, butane is a 4-carbon compound with a functional group of what? Butanone. So one means the functional group of ketone. Aldehyde is shown by al. This is shown by oic acid prefix, suffix, and alcohol is shown by ol. So the one is representative of a ketone group. What is homologous series? Explain with example. So homologous series, as you've already studied, is a series of compounds which have the same functional group substitute hydrogen. So whenever there's the same functional group and all with a different number of carbon atoms, then it is called as homologous series. The example can be alkane. So alkane is a homologous series with members like methane, ethane, propane, butane. The general formula, there's always a general formula for a homologous series. The general formula for alkane is CnH2n plus 2. And that is how you derive the formula of the homologous series. So based on the formula, we have methane, ethane, propane, butane, and you see that the commonality here is that you are continuously adding a CH2. So a CH2 is added, then another CH2 is added, and so on it goes about. So that is how the structure of a homologous series comes about. That is all for this portion. Thank you.